Hello everyone, my name is Deepak, and what I'm about to show you is my project presentation for EL6509 wireless communications. It took me about a month to finish this project and the paperwork related to it. So without any further ado, let me get started on it. The name of the project is Capacity Calculation for the Uplink Channel of Mobile WiMAX with Shadow Fading. And yeah, that's my name of the port. Well, let me first explain what WiMAX is. So as you can see, it stands for Worldwide Interoperability for Microwave Access. WiMAX is an IP-based wireless broadband access technology that provides performance similar to 802.11 or Wi-Fi networks with the coverage and quality of service of the cellular networks. It's mainly intended for wireless metropolitan area networks. So WiMAX can provide broadband wireless accesses up to 30 miles for fixed stations and around 3 to 10 miles for mobile stations. So in contrast, the 802.11 wireless local area network standard is limited in most cases to only 100 to 300 feet. Now, the WiMAX family of standards concentrate on two types of usage models, a fixed WiMAX usage model and a mobile WiMAX usage model. The basic element that differentiates these two systems is the ground speed at which the systems are designed to manage. In this project, I actually deal with the more recent of the two, that is the mobile WiMAX. So, coming to the problem statement, in the past, Shannon's information theory provided a base for study of the performance limits in communication. After this, Somek and Shamai incorporated fading in the Wiener model, which was somehow approximate to the real-world cellular systems. But still, the model was not up to the mark, since the assumption of a hyper receiver would delay free access to all cell site receivers, and the interference pattern assumed by them was the same as the Wiener model. Now, they transferred the two-dimensional model into an equivalent linear system in order to arrange the fading coefficients and the system's path gain in the channel matrix gain. Then came along Letsabes, who modified the one-dimensional version of the Wiener model to account for the free space path loss between the user and the receiver. The optimum capacity of the system was estimated by the Shannon transform. Now, the users were assumed to be accumulated at the cell site receiver position. This accounted the interference not only from the two neighboring cells but also from all the cells in the system. Now, none of these, however, analyzed the uplink capacity of the mobile WiMAX channel, something that I've tried to do in this project. As you'll see, the calculation of the capacity was performed in a real-world scenario by incorporating the log normal shadowing in Gaussian multiple access systems and also in the mobile WiMAX systems. The methodology. Now, I've divided the project into three main modules. In the first module, the input-output equation and the distance-dependent path loss were defined, and some real-world system parameters such as the fast fading and the log normal shadow fading were incorporated. Now, in the next module, the capacity of the system for two different cases, that is, the capacity without shadowing and the capacity with shadowing, were analyzed. In the third module, the capacity of the system in case of mobile WiMAX, along with the shadowing components, was analyzed and the simulated results were observed. Now, the three modules have been implemented in MATLAB, and I've used two files for the code. Let me just open them up first. So, right, yeah. So as you can see, I've commented the code in sort of self-explanatory way. Now, what I've done, I've divided. Like I said, I've used two files for the code. So this is the first one. I just named it as main procap.m. So what I've done here is I've taken the cost 231 HATA model, and what I've done here is I've calculated the path loss, which you can see over here, and then I've used the fast fading model. I've created some noise, and I've used the shadow fading model as well. So I've calculated the value of H, and I've also done the capacity calculation. Now, what I've also done is the distance-dependent path loss, and I found out the PDF of the path loss. Now, the capacity with the shadowing is found, and the PDF of the shadow fading components is found as well. And then I've found out the PDF of the shadow fading coefficients and the capacity versus the cell radius with no shadowing. Well, I've used different values of the deviation and the path losses, and I've plotted the graphs at the end. So yeah, and well, towards the end, I've used it with no shadowing, and I've formulated, I've computed the graphs for the power versus the capacity, and yeah, I've done the same thing. I've changed the values of standard deviation and the path losses, and I've plotted the graphs here as well. So let me just run this. Add to path, and yeah, here we go. Let me just keep these files apart. Away for the moment. I'll be explaining them all, in a while. And well, this is the second part of my program as such. So it's the same thing, it's the same way. I've commented it, for it to be self-explanatory again. So what I've done here is initially I found out the PDF for the random user position, and then I've formulated the path loss model for between two base stations, and also the path loss between one base station and another user terminal. So yeah, I plotted the graph between the path loss and the distance. Here, yeah. Second part would be I found out the channel capacity calculation. I've done the channel capacity calculation for 8 antennas and 1 antenna with different standard deviations. So, and yeah, at the end I plotted those as well. So just running these, and voila, yeah, they're working. So like the previous thing, I'll be explaining the graphs from the PPT. So let me just go full screen. Okay, yeah, simulation and results. Okay, let me get first started. First, this graph shows the relationship between the path loss in dB and the distance in meters. So the parameters that have been used here are L0 is equal to 10 to the power minus 3.8, and R would be equal to 10 kilometers, and R0 would be equal to 1 meter. From the above graph, it could be observed with the variation in distance, where the path loss increases with the increase in distance. So it's also observed that the path loss component increases, attenuation increases for the same distance traversed as well. So when this path loss model is compared with the empirical model, well, that is the Hara model in this case, the value of eta comes out to be between 3 and 4 for the given parameters. The next slide is just going to explain that. So for the second figure, well, the second figure is a plot of the PDF of the distance dependent attenuation with the variable path gain values. And it's observed from this graph that for a given specification of the coverage area, which is 3 kilometers and the path loss factor of 3.5, the user experiences a path loss in the range of 0 to 15 into 10 to the power 7, depending on his distance from the base station. Well, like previously mentioned, the parameters that we use here are L0 is equal to 10 to the power minus 3.8, tau is equal to 3.5, and R is equal to 1 meter. Now, well, the same thing has been explained here as well. So, the third graph. Now, this graph shows how the coefficient of the shadow fading varies with the total path gain. From the graph depicted, it could be observed that the coefficients for shadow fading are low when there is no shift. And as the shift increases, so do the values of the coefficients. Also, it could be noticed that coefficients keep increasing until the value of the path loss. After it reaches that point, however, it starts decreasing again. Well, this graph depicts the plot of how the capacity varies with the varying cell radius. The following parameters, the parameters which have been actually used in obtaining the graph are k is equal to 80, n is equal to 10 to the power 7, p is equal to 300 into e to the power minus 3, d varies from 0 to 3500, and tau takes the value of 2. Now from the graph, it could be observed that the capacity of the system declines with the corresponding increase in the radius of the cell. Also, for the case when there is no shadowing, the capacity of the system is found to be maximum. It increases as the shadowing value increases. Alright, so yeah, this graph is the plot between the capacity per every cell in the cluster and the user power. It helps in analyzing the variation of the capacity of the system as the user power varies. In order to obtain the required graph, the following specifications have been used, that are k is equal to 80, n is equal to 10 to the power 7, d is equal to 3000. Now P varies from around 100 milliwatts to 200 milliwatts, and tau takes the value of 2 to 4. Now this graph is obtained for the given cell radius of 100 meters. For the power of the user varying from 100 milliwatts to 200 milliwatts, the capacity of the system slightly increases with a simultaneous increase in power that is transmitted. Also, it's inferred that the coefficients of the path loss have a greater effect on the capacity of the system than when compared to the change in the standard deviations. Right? Okay. This graph depicts how the value of the path loss varies with the change in the variation of the distance under the mobile WiMAX environment. The following parameters have been utilized that are the height difference between the antenna at the base station and the average height of buildings. Well, the operating frequency has been taken as 2.6 GHz, and from the graph that's been derived, it could be observed that as the value of the distance increases, so does the path loss. Also, it could be observed that for lower values of the attenuation factor, the loss is lesser. Now, as the factor increases, so does the loss. Now, this graph plots the capacity of a mobile WiMAX system with respect to the radius of the cell. The parameters that have been used here are that R varies from 0 to 3000, capital B that is equal to 8.75 megahertz, H is equal to 0.1123, and yeah, that's it. So the figure that let's say the plot actually helps us in inferring that as the value of the radius of the cell increases, the value of the capacity of the cell decreases. Also, it could be inferred that as the capacity of the cell system having 8 receiving antennas is more than the capacity of the system which has just one antenna. The standard deviation is seen to increase as the capacity of the system decreases. Also, the capacity of the system having only one antenna is lesser than that compared to the system with 8 antennas. Yeah, and finally for the conclusion, well, in this project, the uplink capacity of a Gaussian multiple access channel and the mobile WiMAX have been calculated with the help of the Shannon equation. The capacity calculation was performed in a real-world scenario by incorporating the log normal shadowing in a GMA system and also in the mobile WiMAX system. From the simulation, it is also observed that as the shadowing increases, the capacity of the system decreases. So, well, that brings me to the end of my presentation. Thank you for viewing the video.